Thank you very much for inviting me and giving me a chance to talk about my recent work. Here, I will talk about 5D EM symmetry through the toric-like diagram. I will explain what is toric-like diagram later. So this is my first time in Taipei, and I see a lot of signs in Chinese, of course. And then I thought, why not just putting my name in Chinese character? This is my Chinese character. Probably you'll recognize it. But in Korea it says Sung-Soo Kim Sung-Soo. Okay. So when you think about the five-dimensional gauge theory, the first thing that probably you have in mind, including the phenomenologists, is that there's a gauge coupling, which is dimensional full. So in general, it's not renormalizable. So it's not very interesting, or it is cutoff theory. And UV and IL is not well connected. So you make this cutoff. But in 96, Seiberg said that there's some supersymmetric theories, it's well defined, and even in dimension fluid parameter, there is fixed point at the UV where the everything becomes zero. I mean, the coupling goes infinities, and in this UV fixed point, coupling becomes very strong, and the fixed point is realized. So, but what kind of supersymmetric theory that he had in mind? So he had in mind n equal 1, which is A supercharges, and there's many gauge groups, but here in particular, there's SU2 gauge group. With the NF flavors from 0 to 7. But this is, if you are familiar with 4D n equal 2, and this is exactly sort of the related. And also 1,0 theory that just Professor Chu mentioned. And the particular content is that, okay, let me just go review a little bit of this theory. So there's vector multiplier in adjoint representation. There's adjoint scalars. You have also hypermultiplier. There's a 4 scalars. It has SU2R symmetry. And as I said, there is a non-trivial fixed point and UV. And this, where the coupling is really, really strong, infinite. So in IR, the global symmetry is SO2NF. NF is, again, is a number of flavor. And then U1. U1 comes from the topological charge in 5 dimensions. The current is given like this form, and by integrating out these currents, you get the instanton charges. This is topological. But at UV fixed point, the global symmetry enhanced from SO2NF times U1 to ENF times 1. So rank of this NF coming from here, and there's another rank from here. So at UV fixed point, there's an enhancement of global symmetry. So probably you all may be familiar with the EN symmetry. The EN symmetry, what I'm talking about, is the usual EN E7, E6. And it's coming, the terminology over a lower EN coming from this EN thinking diagram. By chopping out one of the nodes, you get the E7 and E6, and E5, which is SO10, etc., etc., etc. Okay. So we want to understand the EN symmetry from the string or M theory point of view. But before that, field theoretically, one can compute the superconformal index at the UV fixed point, and that actually captures the EN symmetry, which I also did with Kim Young and teacher KIAS. This will be also mentioned Toshiagi's talk, so I will skip this, but rather I'll focus on the new work that I've done. So the question is, how do we see this EN symmetry from a sort of the string picture or M theory picture or brane picture? So especially branes are very useful in relating string dynamics to the lower energy phenomena. Especially the gauges theory is realized as effective low energy description of the brane. So in this talk, I will use a PQ web. I will explain what it is and a type 2B brane configuration. I will describe how the gauge theory is realized and compute the Seiberg-Witten curve, which is the single FY brane configuration, and check the EN symmetry here. So this is a brane construction of 5D gauge theory. But we introduce an S5 brane. Whenever we introduce branes, we basically break the half supersymmetry. So they're introducing an F5 brane, we break half. So from 32 supersymmetries, we have 16, and we also introduce a D5 brane, so we'll get break another half. So we have 8 supercharges. So this configuration gives you so 8 supersymmetry configuration. So this is the brane configuration given the coordinates. So NS5 is spanned from 0 directions to 5 directions, and D5 is spans from 0 to 4, and also skip the 5th direction and then on the 6th direction. These from the common direction is one volume of the 5 dimensions, and here this 5 direction the coordinates is often related to the coordinate function is often related to the scalars in the gauge theories. So in this 5th direction, it gives you adjoint scalar in the vector multiplex, and the 6th component of the gauge field, and together with 789 coordinate function gives described hypermultiplex. So choosing some coordinate here is basically is choice of the vacuum expansion value, which is like a Coulomb branch. But this configuration is not actually correct, because when you think about the brane ending on brane, you have to make sure the charge how the charge works. So it turns out the correct charge configuration is something called PQ. So here I have a D5 brane. This is like electric. You can think of it as the electric. It has electric charges. Or there's an S5 brane. You can think of it as magnetic charges. And when this D5 brane ending with an S5, so there's a flux. The flux is constant. So in fact, it flux never electric charge D5 brane flux never diluted. So it should be some sort of there should be some sort of the bound state I call 115 brane. You can think of it as a bound state of D5 and S5. Okay. We can also think about in this way. So the Q is like a charge of electric charges, magnetic charges, etc. And at this junction, the charge is that charge is preserved. Okay. So here, the gauge theory is described in this way. There is a open string that connects this and that. They describe the vector multiplex, and there's a D1 brane that describes connecting an S5 to another S5. This is instanton, etc. So this PQ plane is a plane of x to the 5th and x to the 6th direction, and the non-trivial things happens here. So when I talk about the Seiberg-Witten curve, I mean I'm thinking of the M5 brane configuration expressed in the elliptic curve. So from this, you basically compactify in a circle, and then PDLA to type to A, and then uplift to the M theory. Then you get something like a single M5 brane configuration, which is described by Seiberg-Witten curve. So this is what I mean by Seiberg-Witten curve. So to obtain the Seiberg-Witten curve, it is known that the easiest way is probably from the PQF is to compute the curve from something called dual diagram. So here's the like a PQ diagram, and the dual diagram, I mean, if there's a face that corresponds to dots, if there's edges that correspond to the sort of the line connecting the two different dots, if there is a vertex like this, that corresponds to triangles. Okay. So, and the number of Coulomb branch is number of internal dots. For example, here we have a dimension of Coulomb branch is 1, and here so we have one internal dot. So given this information, what we do is that we basically construct some sort of the equation. So given these directed coordinates t and w, which actually comes from the when we think about the Seiberg-Witten curve compactifying one of the directions and M0 circle, etc., etc. So given this coordinate, so what we have is we write the equation like this, and giving non-zero coefficient, and then determining the non-zero coefficient that basically gives a Seiberg-Witten curve. For example, here this dot is associated with the t to the first power and 0th power is w. So this would be like this C10. So for example, this point as well, this one is associated t to the first power and w to the first t to the 0th power and omega to the first one. So you get something like this, 0, 1. Okay. So basically, determining this coefficient gives you Seiberg-Witten curve. But let's see for the practice. Let's see how do we get the how do we determine this curve? For example, here we have 5 parameters. As this is a equation, you can choose whatever the coordinate system you want. So you can shift to the t direction, also this w directions. So also, as this is the equation, the overall constant doesn't matter. This actually gets 3 rescaling redundancy. You can get rid of, you can choose 3 of the coordinates as you want. And there's a 1 Coulomb modulus which you cannot determine. So this is a parameter of the theory. Then you just remains the one remaining parameter. This is associated with the couplings in the theory. So in this way, you can determine the curve. Okay. So what I'm going to talk about, what is missing in the EN Seiberg-Witten curve. So let me just go through the sort of the small history associated with the EN Seiberg-Witten curve from the seminar work of the Seiberg-Witten and Minahan and Mashansky. They found the isolated theory. With isolate, I mean that there's no Lagrangian description, but there's a symmetry. There's E6, E7, and E8 in 4 dimensions. And 1 year later, with Warner, they uplift this theory, having this symmetry, E6, E7, E8. Okay, and Eguchi-Gano and Eguchi-Sakai, they found manifest, EM manifest curve with a different way from the pre-potential, etc. But I'll talk about this here. And Benini and Benichi Tachikawa, they found sort of the web diagram also connects to the Seiberg-Witten curve for TN diagram. TN is something that N and phi ring wrapping sphere with SUN, 3 SUN punctures, but this is not very important for this talk. And these people, the Yagi here as well, they also compute the E6 curve based on the toric T3 diagram. They check the discrete E6 via symmetries. Okay, so what is left is E7 and E8, which will be the main topic of the what I'm going to talk about. So for that, I'll need to introduce a flavor. So the way they introduce a flavor is basically introducing semi-infinite d5 rings. Okay, so here I have like a naive picture. So we have the gauge theory, pure gauge theory, and we have d5 rings here and here. This could be like a 2-flavor brain configuration. But correct configuration, preserving charge conservation will be like something like this PQM. Okay, and every junction has a charge conservation. Okay, and then open string, the fundamental string connecting this this D5 and the flavor D5 would be describing flavors. Okay, so this is an example again for NF equals 1 with 1 flavor. It's like this, and corresponding toric diagram or dual diagram looks like that. Okay, this is n equal 2. You just add 1 more, so you get this 2. Okay, you can actually do proceed. But if you observe this, as I said, this D5 range is basically the flavors. But I can also say that it's I can introduce a D7 brain where this D5 range ends on. So introducing 7 brane like this, okay, with this configuration, so this doesn't break any supersymmetry, and you can always introduce it. And then position of D5 brane, or more generally, PQ5 brane can end on PQ7 brane. The position of the 7 brane is not actually doesn't affect the physics. So this pure SU2 diagram I rewrite with the 7 brane configuration like this, and then print the 1, 0, 7 brane. This basically describes the flavors. Just introducing one is one flavor. Okay. So introducing the 7 brane actually is very interesting because of the property of the 7 brane. The 7 brane is magnetic charged on the axial dilaton in type 2B. And this is SL to Z invariance, and this is a branch cut. Because of the branch cut, there is a monodromy matrix given in this way. So if there is a PQ or PQ7 brane or PQ5 brane, that of course is counterclockwise. This branch cut, and the sign changes to PQ to P prime Q prime, given this monodromy matrix. When this guy is passing through, not passing through this branch cut, but going this direction, it doesn't change. Only the charges changes when when the object is going through 7 brane monodromy cut. Okay. So for example, this is a 2 flavor case. So I have this pure SU2, and then adding the 2 1,0 7 branes. I deform the theory. I'm giving the mass deformation, and I will. This is a branch cut, by the way, and I will take this to infinity. First of all, I think I forgot to mention. So when I introduce 7 brane, I mean at the end of the day, I will take all 7 branes to the infinity. Okay. So if I bring this one to the right, for example, from here. So as from here, the point where this 1,0, 7 brane meets, from here to here, that actually it's going through the 7 brane monodromy cut. So it changes to this, and because it's a process of the brane passing through brane, there is Hanani-Witten transition, and there's a creation of the brane. Okay. So you can also think about it in reverse way. You first take this as 1,07 brane to here, and then you know that there will be a Hanani-Witten transition. So you will have one brane is created, and then you require that junction. The charge should be conserved. So and charge should be preserved. So you can imagine the resulting the brane. It should be like this. Okay. Okay. So so in this way, you can have like a 4 flavor case. Depending on the mass deformation, you can have this one. But if you now add one more flavor, that would be a 5 flavor. So I introduce this red dot indicating 1,0 brane. So in this way, as a second, as I said, we'll take this everything to the infinity. But if you take this to here, and then you will end up with some sort of crossing. So we have to make sure that how does it work with the crossing of this brane. So there is one way is to bring this. This is a 0,1 brane, 0,1 brane to down here, and then going through a monodromy, or you can also have this Hanani-Witten transition, and you go further here, then you end up like this. In this way, there is 3 branes parallel to each other. There's another 3 branes parallel to each other, and there are another 7 branes are parallel to each other. That actually gives a symmetry group, which is there's SU3, and there's SU3 and SU3. So as I said, this is a 5 flavor, and then it shows in this configuration has SU3 cross SU3 cross SU3, which is maximal complex of algebra E6. So to see that this sub-maximal complex subgroup, you do the introducing extended Dicke diagram and chopping out one of this, and there's SU3, SU3, SU3. So in this diagram, E6 symmetry is realized as a maximal complex of algebra. Okay. So another one is that instead of bring this one the 0,17 brane, I will push this 1,7 brane up. In this case, I will have the monodromy matrix like this. And also this is already connected, is already connected 1,0. And there is a creation of the Seiberg-Witten due to the Hanabi-Witten tradition. But this one, there is a jumping. This is a very particular particular configuration. This jumping can be understood as sort of like a usual brane junction with a very shrinking limit of this. But configuration as it is, we introduce a junction like this. Okay, then it looks like that there's 3 parallel branes. There's another 3 parallel branes, or there is. So the symmetry structure is SU3 plus SU3, and then S of the SU2 plus U1. So this also can be seen as there's a 1 Coulomb branch, there's another Coulomb branch, but it's a very particular limit, very strong coupling limit. Okay, so actually this shows the sort of duality structure known as Edler-Seiberg duality. So one way from this, starting from the 5-flavor theory, so we get this E6 theory. Also, we get some 6-flavor theory with a very strong coupling limit of the SU3 gauge group. Okay, and the corresponding toric diagram is like this. For this to describe this jumping, we introduce not a usual black dot, we introduce a white dot. Okay, this we call a toric-like diagram. Okay, so property of the toric-like diagram is okay. So given these two always can be connected, the Hanabi-Witten transition. So when we compute the Seiberg-Witten curve, as I said, we associate with the non-vanishing coefficients of the sum equation. So on this level, okay, this is the W-axis, this is the T-axis. This level, we have the 2 positions. They look like this is quadratic equation. Here, as they are coincide and binded by a 1,7 brane, the configuration looks like this degenerate quadratic equation. Okay. So, and then I move to 6-flavor case. This is exactly the same thing. So I more or less explained how it works in the 5-flavor case. So 6-flavor is just straightforward. We introduce 1, 2, 3, 4, 5, 6, 1,07 branes. I do the I play with the 7 branes, and I get something like that. So here I have 4 are parallel to each other, and another 4 are parallel to each other, and 2 are parallel to each other. Here the symmetric group is SU4 and SU4 and SU2. This turns out that it's a maximal complex of algebra of E7. So in that way, so 6-flavor has a symmetry of the maximal complex of algebra E7. And you can check this is indeed has the E7 symmetry. So, or I can play with that, pushing this one upward. I have a different configuration. This one has 4 parallel, and another 4 are parallel, and also it looks like that there's also 1 Coulomb branch, there's another Coulomb branch, and the last one, and 3 Coulomb branch, and with a very special limit. And so it gives another dual picture for this 6-flavor case, and the E7 theory can be also due to a very strong coupling limit of SU4 with 8 flavors, etc. So for practical purpose, we take the we push all the this 0,1 brane to the one side and get something like this, and we have 8 of them, and this one actually has the well fits in the SU8 symmetry. So if we write down the curve, then it looks like we have SUS manifest curve, but this one will be invariant under the E7. The way we see this E7 invariance is that we look at the Eguchi Sakai's E7 manifest curve. Okay, this is a elliptic curve, and write this something called J invariance, and then you write J invariance, and you decompose the this is all the characters of the E7. You decompose E7 into SU8 and write this, and then you can compare with the the J invariant of this curve, and you can see that they exactly coincide each other. So in this way, we can see that there is a E7 symmetry for this sixth flavor. Okay, although this is a manifestly SU8, but symmetry is actually E7 invariant. So the conclusion is that we consider the 5D SU2 gauge theory. The global symmetry is seen from the J invariance of the elliptic curve, and we saw that this is disagree. And then for seventh flavor case, we also checked. This is more complicated, but the idea is exactly the same, and you can get the E8 symmetry for seven flavors. So we also discussed about the toric-like diagram and the property of this as the very special limit of the usual toric diagram. Also discuss the dual description of theory. Okay, I will stop.
Thank you, speaker. Questions in the audience? Well, I have a naive question. When you say this NF, this is the flavor, what we are talking about, first generation, second generation, third generation. Is that in the same concept?
So when I say the NF,
yeah.
Yeah. So this is sort of the yeah. I think yeah.
Yeah. Okay. So
So
in that case, then the construction is obvious. Saying, oh, okay, experiment is 3 generation. I only work with n equals 3, n f equals 3, and then the rest is just I mean amusement. Yeah.
Phenomenologically.
Yeah.
Well, this is 5 dimensions, so I don't know. First of all, how it relate to the 4 dimensions. But the theory is also related to 4 dimension n equal 2 theory. So in that case, I think the number of flavors goes all the way to 4 generations probably. But I'm not sure whether there is a phenomenology associated with n equal 2. Probably not.
Okay. So other questions? Yes.
Can you say something about the 5D theory obtained from M theory on the O-3 bundle over P2? So that formally corresponds to the NF equals to -1 case.
So you're talking about the
That one doesn't have any global symmetry.
Yeah, E0.
E0.
E0 has U1 global symmetry.
Oh, right.
Yeah.
U1.
Right.
So like.
So I don't think it's a gauge theory. It has. So here I skipped the one. You can have the E1 tilde here.
Yes.
And so these flavors can be understood as a mass decoupling limit from you take the one of the mass with infinity, but from actually it stops here. So you actually the E1 tilde. Yeah, E1 tilde is actually connected to the. There is a two theory E1 and E1 tilde, and E0 theory is not coming from the E1 but E1 tilde.
Okay.
But E1 tilde is not a gauge theory. It just has rank 1, but not a description of the gauge theory. And I'm not sure that how the brain description works from the type 2A picture.
So we also don't know the Seiberg-Witten.
Oh, we know the Seiberg-Witten. We know the Seiberg-Witten.
Yeah. So details will be later for discussions. I mean.